So the first video from chapter 8, we're going to talk about current and current density, and this covers chapter 28.2 and 28.3 in the textbook. Okay, so first off, let's look just a little bit about how charges actually flow in a conductor. So we've talked about conductors, and I've always made the statement that charges are relatively free to move around in a conductor, but what exactly does that mean? So in a conductor, you have something called conduction electrons. And the conduction electrons are electrons that can travel from atom to atom. It's not like they're just freely moving around, so they're actually bouncing back and forth from one atom to another atom. Now, and in conductors, so these electrons have thermal energy, and the thermal energy is large enough that they're actually able to jump around from electron to electron, so they're not bound to a particular atom. However, right, if you don't have any net electric field or anything like that, they bounce around from atom to atom, but there's no net movement, right? So you imagine you've got all these little electrons kind of randomly just moving about from atom to atom, but there's no net movement from one place to another. However, if you apply an electric field, that will actually cause a net motion. So for example, on the picture on the left here, so we've got an atom that's just bouncing back and forth between a whole bunch of different atoms, but the average position actually doesn't change in time. It's just randomly moving about. Now for this on the right, so now we've got an electric field pointing to the left. So this is an electron, so it's negatively charged. So it's still bouncing around, but you wind up with a net movement to the right, since the electric field is to the left and our electron is negatively charged. So, and that's kind of an important thing to realize, that in these conductors, we talk about charges being free to move around, but they really do just bounce back and forth from atom to atom, but there is a net movement, right? And another important thing to remember is the electrons are actually moving very fast. So something like 10 to the 6th meters per second in between collisions. But these collisions happen very, very frequently. So if you look at the net speed, or sort of the average speed, or average displacement, I should say, so that's actually quite small. And usually you call that the drift velocity. And the drift velocity is more like 10 to the minus 5 to 10 to the minus 4 meters per second. Okay, so now we can define current. So typically we're going to use something called the conventional current. So the conventional current is we have positive charges moving from high potential to low potential. Now, however, in reality, we know that it's the negatively charged electrons that move in the opposite direction, so from low potential to high potential. However, as it turns out, we can do pretty much everything we need to, in this course at least, without actually knowing that it's the negative electrons moving in the opposite direction. We're just going to treat it as if it's the positive charges moving from high potential to low potential. So we define current. So current is the rate of charge passing a particular point in a plane. So in the picture here, so imagine we have some sort of a wire. We've got charges flowing in the wire. So we define some sort of a plane or a point along that wire, and we just count how much charge passes that point in a particular time interval. So dq over dt. And so if we think about units, well, charge is measured in coulombs, time is measured in seconds. So the SI units for current is going to be coulombs per second, which is known as the ampere, or often called just an amp. So if we want to go in the opposite direction, so if we know the current and we want to figure out the charge, well, if we just integrate dq, and we can just integrate from 0 to whatever time we're interested in the current with respect to dt. So, and another important thing about charge, so remember, well, it's the electrons, but there's these charge carriers that's carrying the charge around, and they just don't disappear or magically appear from nowhere. So charge has to be conserved. So let's say you have a wire that branches off into two other wires. So the total current has to add up. So charge is conserved, it doesn't just disappear. And also current is a scalar, so it has to follow the direction of the wire. Although sometimes we do talk about current being positive or negative depending on, right, if it's going one way along the wire or in the opposite direction along the wire. But current is a scalar. So we can define a vector though, and the vector is called current density. So current density is a vector quantity describing the macroscopic flow of charge. And current density, which we're going to use a J to stand for current density, I guess because it comes after I maybe, I don't know. So, but J, the current density, is current divided by a cross-sectional area. And current density is proportional to the electric field you apply. So the units are going to be, well, if current is in amps, area is in square meters, so it's amps per square meter. It's going to point in the direction of the electric field. And if you have a wire, so the current density is going to be related to the drift velocity. In particular, the current density, which is a vector, so it's the number of charge carriers times the charge on each of the charge carriers, right? So it's just charge on electron times the drift velocity. Right, so N is the number density of atoms in the conductor, so it's basically the number of charge carriers you have. And so here's one way to think about it. So you have a wire, you've got all these little charge carriers. They have some drift velocity, and your current density has to be in the direction of the electric field.